try hard algorithms, people. No natural calamity can stop you from coming. Fight the power.
What things are there?
Okay, so today and tomorrow we will just do some problem solving to prepare you for the midterm next week. So let's just quickly revisit the problem that we started last time. So you have to multiply two polynomials. P of x is equal to a0 plus a17 x to the 17 power plus a19 x to 19 power plus a23 x to the 23rd power, and q of x equals b0 plus b17 x to the 17 power plus b19 x to the 19 power plus b23 x to the 23rd power. And let's first see how to do it with 16 multiplications, and then
I think it's last week we had a 21st pair as well.
oh, you're right. Sorry. So a21, 21 plus a23 x to the 23 plus b19, no, b21 x to the 21 plus b23 x to the 23. Okay? So first we want to do it with 16 large number multiplications, and then try to do it with 12 only. Right? So the easiest way of doing it with 16 multiplication, we simply write p of x as a0 plus x to the 17 power, and then you have a17 plus a19 x squared plus a21 x to the 4th plus a23 x to the 6th, right? And let's call this polynomial P1 of x, and we have the same for Q of x. It will be of the form B0 plus Q1 of x. Right, so this is A0 plus x to the 17 P1 of x. Okay, so now if we multiply P times Q, we have that P of x, Q of x is equal A0, B0 plus, and then what do we get? We have x to the 17 times, and then we have B0 times A17 plus A19x squared plus A21x to the 4th plus A23 x to the 6th, right? Plus, and then the same, but with the exchange roles of A and B. So it will be A0, and then we have B17 plus, you know what's here, plus B23 x to the 6th. So now how many multiplications do we need to execute this? was too enthusiastic. Okay, so what do we have now? We have one multiplication here, right? Oh, we haven't finished the whole story here, right? So that's this part, and then we have plus x to the 34, and then here we have p1 of x times q1 of x, right? You agree with this? So how many multiplications do we need? Well, here we have one multiplication, and here we have 1, 2, 3, 4 multiplications, and here we have another 4. So, and so this is all together, we have used up 5 multiplications. If I'm not, did I count correctly? No, 9. 4 and 4, 8, and 1 is 9. Sorry about that. 9 multiplications. And how many multiplications do I need to multiply p1 of x times q1 of x? That's right, because this is if I substitute x squared with y, this becomes polynomial of degree 3 times another polynomial of degree 3, and we know the product of these guys is of degree 6, so we need 7 multiplications, so 9 plus 7 is exactly 16. Right? So, how do we do it with only 12 multiplications? What do you think? What is the reason why we can do this with only 12 multiplications? Let's see. When you multiply p of x with q of x, let's see what powers do we get. So p of x times q of x. Let's call this c of x. What powers do we get when we multiply p and q? Well, we have powers 0, which is just a0, b0, right? Then we will have 17, 19, and 21, right? And 23. And then we have 34, 36, 38, 40, 42, and 44, because they all grow by 2, right? So the smallest one of even degree is 34, and the largest is 46. So how many of them is that? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 powers. So what is our polynomial like? Well, our polynomial will be now of the form c of x is equal c0 plus c17 x to the 17 plus c19 x 19 plus and so forth plus c46 x to the 46, right? Now, how many coefficients? There are altogether 12 coefficients, because these are the powers, 0 up to 46. So there are here only, in fact, maybe I should write C0, C1, C2, up to C11, right, starting with 0. So there are 12 numbers to determine. So how many values do we need in order, how do we get these coefficients? Well, we could in principle compute 12 different values. So maybe for x equals from, say, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, that's 11, and 6, right? So we can compute p at, p at xi, where, let's call this set S, for xi belonging to S, and we can compute q of xi when xi belongs to S, and then we can compute p of xi times q of xi, and this is exactly c of xi. Right? So now you will have how many? 12 many values. Right? And you will have how many variables? You have 12 unknowns, right? And 12 equations to solve. Right? Because we have only 12 distinct values of c, so there are 12 variables here, right? You will have something like this, c0 plus c1, and then here -5 to the power 17, plus c2 -5 to the power 19, plus c11 -5 to the power 46, right? And so this will be just the coefficients, because these are just fixed numbers, right? And this will be equal to p at -5 times q at -5. So we will get altogether 12 equations with 12 unknowns to solve. But there is a problem. Why does this system have a solution at all?
Yes.
Unfortunately, no. Now, this is what we want to see next. So the moral is 12 values is enough, but you have to make sure that the system of equations is not singular, that it has a unique solution. When does a system of equations like this have a unique solution? When the matrix is non-singular, when you can invert it, right? So let's look what the matrix is like and then see why it's actually singular. So we will need 12 values like this, but unfortunately we will have to pick different 12 values, and that's exactly what we want to see next. Okay, so let me see what can I erase. Are you following everything so far? So, what is the mechanism? We simply reduce finding the product polynomial to inverting from its certain number of its values to obtain the coefficients. And its values are obtained by large number multiplication by simply multiplying the values of the corresponding polynomials p and q. So the general principle is always simple. So you evaluate p at xi and q at xi at sufficient number of values. Then you multiply p of xi times q of xi, right? And this is your c of xi. And then you have to solve back, you have to find the coefficients by solving this system of linear equations, but the mechanism is always the same. From the coefficient form, we move to the value form. How many values we choose? Well, as many values as it's necessary to determine the coefficients. So clearly, the number of values that is equal to the degree of the polynomial plus 1 is enough. But if lots of coefficients are 0, right, because this is very sparse polynomial, it has very few non-zero coefficients, right? There is nothing multiplying minus 5 to the 45, right? So we just want to see that it's not necessary always to evaluate as many values as it's the degree of the product plus 1. Sometimes a fewer number, if the resulting polynomial is like this, fewer number of values are sufficient.
One sec.
Yes.
You're missing a bracket here, so where's that missing bracket? Or
Which
can I see
bracket?
it? Is it hiding behind this silver thing?
Sorry?
After the X17 is bracket.
Yeah, it's hiding behind that.
Yeah. Okay. Sorry about that. Okay, so let's see why choosing these values will not work. Well, what is the system like? And what is its corresponding matrix? Well, the system looks like this, right? The matrix is 1, so we want a matrix so that when you multiply this with the coefficients C0, C1 up to C11, you get exactly polynomial C of x. So what do we need here? So C0 just has to be multiplied by 1. Then we have here, say, x first value. So let's call it, well, let's put concrete values. Say if you put here minus 5, to which power? To power 17. Then minus 5 to the power 19. And I was very excessively optimistic here. Then we have minus 5 to, which are the values 21, then minus 5 to value 23, and then we have minus 5 to the value 34, minus 5 to value 36, and then along these, it's the last one is minus 5 to the value 46. Right? So if I multiply this by C0, C1 up to C11, what do I get? I get C for the value minus 5, right? That's the first. Let me write it as a vector. So this is C at minus 5. And in the same way you will have, now I'm going to order it in a different way. So the next value I want to consider will be 1, and then 5 to the 17, 5 to the 19, 5 to the 21, 5 to the 23, 5 to the 34, 5 to the 36, all the way to 5 to the 46. So what will be here? It will be value C at 0.5, right? So this is our matrix. In the same way you will have, and let's write them always in pairs. At the end you will have 1, what was the last one is 6 to the 17, and here it will be somewhere here 6 to the 46, and this will be C at value 6. right? So these guys, we simply find by evaluating the product of P and Q, right? So this is where the large number multiplications are hidden, right? Because this is, what is this? This is equal to P at minus 5, Q at minus 5, all the way to P at 6 times Q at 6, right? Okay, so now we have 12 values here, but the problem is, and we would like to get the coefficients, so what do we have to do? We have to multiply these guys with the inverse of this matrix. But the problem is that this matrix doesn't have an inverse, because its determinant is 0. So why is this it's easy to see what happens if I subtract the corresponding pairs. What happens if I multiply this row by minus 1 and add it to that row? You see, all of the even degrees, so if I multiply this by minus 1 and add it to this, what will happen is the following. All even degrees will become 0, right? Because negative 5 to even power, sorry, this is not visible. So these guys will become 0, right? So what will happen? This will also become 0. So I'll have only 1, 2, 3, 4 non-zero entries, right? So if I do this transformation, my matrix will start looking like this. My matrix starts looking as 0, and then here it will be minus 5 to the 17, minus 2 times 5 to the 17, right? Because minus can go outside, and this is multiplied by minus 1, so it's minus 2 times 5 to the 17, minus 2 times 5 to the 19, minus 2 times 5 to the, what's it, 21, and then minus 2, 5 to the 23, and then zeros everywhere, right? So this looks like this. This vector looks like this. 0, and then something non-zero, 4 of them, and all other are zeros. And how many pairs I have? You see, I have 5 pairs because x goes from, say, from 1 to 5. I have 5 pairs. So I will have 5 vectors that look like this, and then 0 everywhere. Right, and the last one, the 5th one. So can these 5 vectors be linearly independent? So I have 5 vectors that are 0 everywhere except at 4 places. What is the dimension of the vector space spanned by these vectors? At most 4, right? Because there are only 4 non-zero coordinates. So you have 5 vectors in a 4-dimensional vector space, and they have to be linearly dependent. So this matrix is, the determinant of this matrix is singular. Its determinant is 0. So what do we have to avoid? We have to avoid forming 5 pairs, so that this no longer works. And lo and behold, if you want, you can experiment with Mathematica. If you take for S, say -7, and then -4, up to 1, up to 6, then you will have only 4 pairs. You see, so this 7 has to be larger. Taking -6 here will not work because it will pair with this one here. But if you take -7 and then the rest up to here, one can verify that the corresponding matrix, so just imagine here -7 rather than -5, the corresponding matrix is non-singular and you can solve it. So in principle, there are only 12 multiplications needed. But from practical perspective, look, essentially you have to evaluate polynomials of a large degree. The degree was 23, right? So it will be -5 to the power 23. So this is actually, even though it's a constant, it's a huge constant. So unless the degree is small, and you can do this Karatsuba trick, you can do it just by solving the systems of linear equations. For as long as the degree is significant, we always use fast Fourier transform to, that of course doesn't have, nothing of this sort appears in FFT. Okay? So do you understand what is happening here? Right? Simply, the product of the two polynomials is sparse. It has sparse coefficients. So there are, even though the degree is 46, we don't need 47 values. We need only 12 values to uniquely determine the coefficients. But you have to be careful at what values you evaluate to make sure that the corresponding matrix is non-singular so that you can invert it.
Alex?
Yes?
So, two questions. First one, where did the 2.5 come from?
2 point, no, this is -2 times. It's not 2.5, it's times.
Ah, right. Yep.
Right, because when you multiply this by -1,
Yeah, that makes sense, yeah.
right?
Yeah. And so what's the relevance, why are you subtracting those two lines?
Okay, so this is just how to show. So the question is, why am I subtracting these pairs? I simply want to show that the matrix is singular. So if I take the values at -5 and pair it with values at 5, and if I multiply this row of the matrix with -1 and add it here, what will happen is that all the even places will cancel out. So you will get zeros on all even powers and non-zero only on odd powers. But there are only 4 odd powers. And if you have 5 pairs, by subtracting the pairs, so multiplying one of them and adding with -1, and excuse me, and adding it, it will produce a row that looks like this. If I have 5 pairs, I can produce 5 vectors that are everywhere 0 except at 4 places. So the dimension, the vector space spanned by these 5 vectors is actually of at most 4. Because there are only 4 places where you have non-zero entries. So you have 5 vectors in a 4-dimensional vector space, so they cannot be linearly independent. But if rows are linearly dependent, this means that the matrix is singular, right?
Okay, and that would apply for any multiple, 1, 2...
It's for as long as you can form 5 pairs of n and -n. If you get 5 of them, so it's just important to make it a little bit asymmetric so that the matrix is kept non-singular. Yes?
What does 0 and 6 pair?
Sorry?
What does 0 and 6 pair?
What?
Oh, so yeah, from the original one. So we got 5.
So you have 5 pairs, 5, minus 5, 5, minus 4, 4, 1, and minus 1.
Okay, but we needed 7 all up, but 2 of those are accounted for by 0 and 6, but then the remaining 5 can't be accounted for.
That's right. Okay, so as I say, in general, the smallest number, if using this method, the smallest number of multiplications is the number of non-zero coefficients on the product polynomial, but you have to make sure that for the values you choose to evaluate the polynomials, this matrix, the corresponding matrix, is non-singular. Yes?
What stops the roots when you do FFT? When you have roots of unity, aren't they in pairs?
But then, you see, that's a very good question. So what happens if you have a roots of unity? What happens is that then the matrix is full and it corresponds to van der Waals determinant, which is non-zero. So if you have all of them, so there is one odd, right, for the value 0, yeah, right? And the rest, what happens with the rest? Only half of them zeros. So if you think carefully, the matrix will be non-singular. So in fact, when you have all the powers, the value of the determinant is the product xi minus xj for all I non-equal to j. That's the value of the determinant. Okay, very good question. So simply there is, when you have the roots of unity, you cannot have that massive cancellations. Half of them will be non-zero, and you will have, of course, additional when you substitute. When you substitute 1, you will have additional that is everywhere 1. Okay, so all that you have to know, just you have to understand the mechanism for how this method of multiplication of polynomials works. It's really very, very simple. Yes?
So if we were to evaluate this using the roots of unity, what order of roots of unity are we?
Well, there is no help. It has to be of a power of 2, so you will have to go to 64.
So it does have
yes.
to be.
Yeah. But it runs in n log n time, so you see, this looks much faster, but the problem is here, just look what the degree is. You would have to compute 5 to a huge exponent, so it's only, so this is what one of the reasons why one has to be careful with asymptotic estimates. Right? This is all linear transformations doable in linear time, right? So you have to just to do limited number of large number multiplications, but there is this explosion in size. The values of your polynomial, if the polynomial is of large degree, are truly gigantic. Now, of course, this is the powers will be constant, but huge constant. So what's the value of an algorithm with a low asymptotic complexity if the constants are huge? Remember, this happened also with generalization of Karatsuba when we split into more than 2 pieces, right? If you split into n pieces, you get this n to the power n. Okay, so let's see just the last one. Last example was the simplest one. But it's kind of instructive. What is the minimal? Can you multiply polynomials? Yes.
For the computation of the really high order, like -5 to the 46. Regardless of what the polynomial is, if it's of that order and like of that form, wouldn't it always use the same powers? So couldn't you just calculate those beforehand? This is sort of
Well, yes, you can, absolutely you can, but they are really gigantic. But it's true, all of this is doable. This can be all pre-computed. So it can be pre-computed, but just the arithmetic involved will be
like multiplying each
yes,
with
yes,
C11.
exactly,
Okay.
right? So it's just a gigantic number, and you know you have to invert the matrix to solve. You have to invert this matrix, and look what are the entries. Just try at home to invert it. Okay, so let's just see. So, and in fact, when we do FFT, the powers of the roots of unity are always pre-computed, right? Because they are just these complex exponentials. Okay, so how would you multiply A0 plus A100 x times B0 plus B100 x to 100 x to 100 with only 3 large number multiplications? If we did the Karatsuba trick, how many values would we have to evaluate the polynomial at? What's the degree of the product? 201. But so if you just did Karatsuba without thinking, you would have to evaluate these polynomials.